Here's a note about the magnetic flux density and the current. So when the magnetic flux density and the current are at right angles to each other, we use F is equal to BIL. The force experienced by the wire is then perpendicular to the magnetic flux density and the current itself. So the force in this case will be out or in to the page. I'll leave you work that one out yourself. Now, if the current is not perpendicular to the magnetic flux density, what you need to do is resolve the magnetic flux density vectors into those that are parallel and perpendicular to the wire. This thing here is the magnetic flux density vector. So we're resolving the vector where each of those can be representative of the vector, and that vector has a magnitude and a direction. So what I've done is the current is still there. I've taken the middle one, and that's the magnetic flux density vector, and I resolve it into two components. One of them is perpendicular to the wire, so I'm going to call it B perpendicular. The other component then is parallel to the wire, as we can see there, so I call it B parallel. And it's the perpendicular component is the one that creates the force. So when we use F is equal to Bil, it's actually the B perpendicular value we're going to put in. Now, because that's a right angle triangle, with a right angle always between the two components, and with this thing here being the hypotenuse, I can use the sine of theta as the opposite over the hypotenuse. So therefore, when you rearrange it, you get the perpendicular component is B sine theta. So perpendicular component is B sine theta. Fill it in and you get this thing. I leave the angles. I leave you work out the angle yourself. Theta is the angle between the magnetic flux density and the wire. They're opposite angles. And this thing then, look, is an alternate angle. You should be able to do that.